Welcome back to this ambitious series. Today in store we've got more Vulkan. As we begin to build up the rendering part of this game, there are so many different graphics and Vulkan concepts that we have to get through, and since I'm trying to be pretty deep and educational, we wind up with videos like this one. Now I decided to keep this one a little bit shorter than the other two just because I feel like there's some processing, like in your brain, would be beneficial. There's basically a lot to take in, is my point. We're going to introduce normals to our cube, which is going to let us light it, which is pretty cool, but it's also going to expand our pipeline a little bit and cover some more theory. But then the kind of juicy part of this video is going to be Vulkan descriptors. This whole concept of descriptors and descriptor sets can be super confusing to people who are new to Vulkan or the more modern rendering APIs in general. Hello, son. Let me just, But trust me, they're really not that bad. They just allow us to access resources in our shaders, and today we'll be learning how to do that with a texture. As always, there are chapters in this video that should help navigating it a little easier. So without further ado, enjoy. Let's jump in and have a look at what we had last time. Over here, I'm running a server on like an actual Linux VPS. And then here I have a client that has connected to this server. In this case, it's uswest.studiocherno.com. Once I've connected, you can see that I can control this little 3D cube that we've made. We've got some like camera controls going on here, nothing too fancy, but you can see that the cube is of course 3D. And then what I can do is run another instance of this and then connect to the same server over here. And then now I should have both of them here. Now I have moved a little bit out of the way, so let's see if I can find myself. Okay, so this is being controlled by this client. Now the camera is not set here, so that's why we can't see it in the second client. But if I move with the WASD keys on the second client, you can see it moves on this first client and they can both move. So that is what we have going on. The plan today is going to be really simple on paper. It's going to hopefully help you a lot with Vulkan and clear up lots of questions and provide you with some tools to actually use the API in a bit more of a powerful way. Because what we're going to do today is we're going to talk about this normal version of the cube, right? So the cube that we actually made and that we have over here does not have normals. It's kind of like a simple cube. We're going to expand on that. And then finally, we'll talk about descriptors in Vulkan, which is like one of probably the most complicated things to beginners. And descriptors are very important because they allow us to use resources in our shader, whether that be buffers or textures. So we all know that optimization is super important in programming and for the project that we're working on. But here's a concept. Optimization is a lifestyle. You gotta optimize every aspect of your lives, and that's where Saily comes in, the sponsor of this video. Saily is an eSIM service from the creators of NordVPN that makes international travel way easier. No more wasting time hunting down SIM cards or paying ridiculous international roaming fees. I think mine is something like $10 a day. No. Just install Saily, pick a plan, and you're online in over 190 countries. That's right, with Saily, you only have to install an eSIM once. You don't need to install a new eSIM for each country. When I'm abroad and need internet, which is like, you know, every time I'm abroad, it usually goes one of two ways. Either I jump from Wi-Fi to Wi-Fi, which is just, I don't know, silly and time consuming and unreliable, or I'm trying to suss out who the best provider is wherever I am, one that's not too expensive. Then I gotta like find a store, give them my details, probably lose my SIM card when I put theirs in. Saily cuts all of that so I can just enjoy my time instead. As I mentioned, it's super easy to set up. You just download the Saily app, you pick a plan. You can see, by the way, just how affordable these plans are. I think these are really great value. And then just use code the Cherno at checkout for an exclusive 15% off. Just click the link in the description below or use the QR code on screen to get started. Huge thank you to Saily for sponsoring this video. Okay, so without further ado, let's shut all of this down. We got a nice little crash on exit, which is great. I'm gonna also just stop the server over here. And then I think the first thing I want to do here, since we're going to be iterating over some actual graphics code, is I want to be able to actually see what we're doing. Because when I launch this at the moment, you can see that it wants us to connect to a server and doesn't actually display anything. The reason why is because we actually have some code over here inside on render, where if the connection status is connected, then we actually render the cube. Otherwise, we don't render the cube. So for now, I just don't really care about this condition whatsoever. So I'm going to comment it out. That should mean immediately that we just render the cube. Now we're not going to have any player data, so we're still not going to actually render the cube. I mean, we should render this cube. Let's have another look quickly. We're not going to render any of the additional cubes as you would expect, but I think the problem here is just that the camera is not set. Okay, so here we go. So we see the cube if we move the camera back a little bit. I think the cube being offset is because the player position starts at 50-50, because that's in pixels or whatever. Like that's how it used to be when we were rendering it in 2D. I think when we actually render the cube, we probably have the, like this cube scale, which I don't even know how that gets set. That's controlled, I think, by IMGUI over here. So we have this scale that gets applied to that position. And anyway, it's a little bit of a mess. I really don't want to do it that way anymore. That was just more to test things last time. So let's just maybe get rid of this cube scale entirely. And then the player position, I'm just going to set it to 0, 0. So it's just at the origin of our world. And then when we render it, we won't multiply the position with cube scale anymore. And we'll get rid of it from the UI as well. So now the only thing that needs to happen is we need to make sure that our camera is actually back far enough for us to see. So if we go to the renderer, we have a camera position. So it's back 3 units. The units we're going to start using here are meters, right? I don't know why I'm doing this in quotes, but anyway, they're meters. So instead of just saying 3 units, I'm going to start saying 3 meters. Now, of course, it's completely up to you to actually add meaning to these numbers. So 3 is in fact just 3 units. It doesn't mean anything unless you decide to treat it as centimeters or meters or inches or whatever. So by me saying 3 meters, that now means that if this cube is a 1 by 1 cube, then I expect it to be like a 1 by 1 meter cube. The reason why this matters at all, really, is when you start making multiple objects and you obviously need them to relate to each other. So if you're making like some sort of building and then you want a person to enter that building, obviously they have to be on the same page as to what the numbers mean. Otherwise, you might end up with a person that's bigger than the building, and that doesn't make any sense. Okay, so now that that's established, let's pull this out a little bit. Maybe like 8 or so is good. So I'm going to come over here to the camera position, set it to 8. We have cube rotation as well, which at the moment doesn't really do anything. I don't know if we have the ability to rotate the cube from the client. I think that might be something we can do. Over here into render cube, I'm just going to really quickly add some rotation as well. So we can take in rotation and position over here. Let's paste that in. And then we're going to rotate the cube. So I think we were already basically doing that with M cube rotation. So instead of M cube rotation, I'm just going to use our rotation parameter. And then if I come over here, I'll just remove cube position and cube rotation because we shouldn't really need them anymore. I think we're setting them over here in render. Were we still rendering some kind of other cube before we, or I think this maybe just doesn't get called anymore. Yeah, it looks like we never actually call that render function. So we can probably just get rid of it, to be honest. I think we do everything else here anyway. So I will in fact do that and simplify the code a little bit. So now we should be able to pass in a rotation. And the reason why I really did that is just because I want the cube to rotate just so that we can kind of see it from all angles, because that's going to become important. So let's make a player rotation. I'll make it a vec3, 0, 0, 0. I'm probably just going to use degrees here. So let's maybe rotate it around the y-axis 45 degrees. Really, I'm probably just going to set this into IMGUI, which we had render or render UI, which was doing all of these controls. Now that we kind of should really be moving this stuff out of the renderer. The renderer class over here, this file over here, is really just supposed to render things. It's obviously not supposed to store the position and rotation of our camera. That should be like an external entity. So that's also something that we should probably move out of here. Doing a little bit of organization and architecture stuff here is probably going to be useful in the long term. Now, the actual camera position is just being used straight up in render cube. We create a camera transform and then we set it as a push constant. I think what I'm going to do here, even though I wasn't really planning to, is I think I'm going to pull this stuff out and I'm going to sort of introduce the concept of a scene in a way. I don't want to go crazy with like architecture here at the moment because I want to focus on what we're supposed to focus on in this video, but I think it's going to be useful for us to do this, and it's going to prevent us from just continually accumulating tech debt and just having messy code, right? So what I want to do is this camera position and rotation. I'm just going to pull this out. Push constants I'm going to leave because they're to do specifically with rendering, and this is in fact the renderer. So I'm going to leave that stuff, but I'm just going to pull out the camera into the actual client layer because this is also where the player lives. So eventually this should go into some kind of scene, and I guess you would want these to be entities in an entity component system. Depending on the scale of your game, this could of course be completely unnecessary, and I think it's worth noting that it's important that you need to decide whether or not you want to architect this like a game engine or specifically like a game. We are going for more of a game vibe than a game engine. Obviously, we're not trying to build a game engine here. So to be completely honest, like an entity component system is probably just not something we need at all for this project. But I would still have some sort of scene system, and that's basically like the kind of end game of where this stuff would reside normally. So camera position, camera rotation are here now. So what that means is we now need some way of communicating this data into the actual renderer. At the moment, when we render things, let's have a look at where that happens. So mRenderer render cube, I think that's all we do. I mean, we initialize the renderer in onAttach, and then we just render over here inside the onRender function. Since we need a way to set the camera, what I'm going to effectively kind of do is introduce like begin scene and end scene. This is just a normal kind of way to architect your renderer where you have your context that's provided in begin scene, and then end scene will normally like submit the command queue for rendering and do all of that stuff. I don't actually know exactly how that's happening at the moment. We just do a draw index. Oh, and the command buffer, I'm guessing, is yeah, directly coming from the actual like application. So this would be the command buffer that is basically responsible for rendering our swap chain. Normally you'd probably have a dedicated command buffer for just the commands to render a specific scene. In this case, we don't, which is probably good for now because it just reduces some complexity, but I'm still going to have a begin scene and I'm going to have an end scene. I think I'm going to introduce the very simple concept here of a camera, and then that's going to be what we actually take into begin scene. So we'll just say const camera. Let me go ahead and make these functions. The camera will probably just be these two, so we might as well just switch to using a camera instance over here, and then I'm going to add in position and rotation like that. I'll just keep the defaults on what they were just to keep things simple. And then basically before we render over here, we should just do, I might do it up here actually. We'll do mRenderer begin scene and then we'll just pass in our camera, and then end scene, really not going to do anything at the moment, but it might in the future. So let's just do end scene over here. So every time we begin a new scene, we pass in a camera. This makes sense because usually you render a specific scene from the point of view of a specific camera. This is also going to basically introduce some sort of optimization here, where instead of calculating the camera transform per cube, so you can see at the moment that we do all of these calculations and we set the push constants, we invert the matrix, we do all of these kind of expensive-ish operations every single time we render a cube, which obviously isn't correct because the camera does not change at all between rendering cubes. We basically set our camera and then we render all of the objects in our scene based on that like camera's point of view. So all of this stuff is now going to actually move out of here and into begin scene, which is going to be definitely a good optimization depending on how many cubes we're actually rendering. Now we probably can't move all of this out. Like the actual projection here is kind of dependent on the viewport width and height, and we want that to change in case the window resizes and the aspect ratio changes. So that's probably something we'll have to think about. The camera transform of course can be calculated here. So we'll just do camera.position and camera.rotation. So let's paste that in like that. We'll just make this full screen. So the inverse of the camera transform is probably something we would want here. To be honest though, even though the viewport width and height, I think we could probably obtain that in begin scene, to be honest, because it's not like it's going to suddenly change during our render cube. We might actually just grab this. I mean, we don't need the command buffer, but we'll grab the viewport width and height. Might actually cut this out of here because that's obviously not something that's specific on like a per cube basis. Let's go ahead and put that over here. So we've got our viewport width and height that we can calculate now. We can set up the push constants. The transform obviously is like a per cube thing. So we definitely wouldn't do that here, which means that we should definitely put that back. Otherwise we're not going to get our cube in the right place. And then bind pipeline is probably something that you could do in begin scene. You wouldn't generally do that because you would have many pipelines in like a renderer. So you would kind of do that on like a begin render pass situation or like a per render pass frequency. Command set viewport, set scissor, all of that stuff can definitely move into begin scene as well, which means that we do actually need the command buffer. So let's go ahead and copy that and put it over here. Really what I'm trying to do is just keep render cube, just render cube, right? Meaning that like, okay, we need the vertex buffer, we need the index buffer, and we do the draw call. That should basically be it. And obviously the push constants are also something that are per cube because we have the transform being set per cube. Bind pipeline, again, not something that should be in render cube, but because we don't have the concept of render passes yet, and I'm not talking about VULKAN render passes because I think we do have those, we have to have those. Our renderer doesn't have a concept of like, this is a geometry pass, or this is like a pre-depth pass, or this is a like post-processing pass or whatever. It doesn't have the concept of that yet. So we'll just keep this here for now. Okay, cool. And one other optimization that I might mention here, just because we're on the topic of optimization, cubes are all going to be the same. And in fact, I have a feeling that most of our entire game world is probably going to be made up of cubes just with various scales. So, I mean, if you have a wall that looks like this, that could still be just a cube, meaning it's still the same geometry, but it's obviously non-uniformly scaled to be like this wide. If that's the case, then you would typically just draw this all instanced. So the command draw index actually already has like an instance count and like a first instance variable. So you basically would just draw this same geometry multiple times. And so you wouldn't have to go through the process of binding vertex buffers, index buffers, doing a push constant per like draw as well. You would have like this big transform buffer that contains this transform for each cube that you're trying to draw, which would of course include its scale, which is its shape. And then you would just draw it. Now, it also depends if it gets getting drawn with the same material, and if materials just mean different textures or potentially different shaders, because that would involve different pipelines, so it does get a little bit more complicated. I think I'm getting a little bit ahead of myself, but that's just something that's worth noting. I mean, this series is supposed to be a little bit deep, so hopefully you guys are enjoying the depth. All right, and then finally we just have a bunch of render UI stuff. I'm gonna cut all of this out from here. We'll leave this function just in case we want to do some like debug rendering things here, but I think in on UI render really is where I'm going to, yeah, like over here, because we used to do render UI here. So let's just bring the controls over here, and then camera position, camera rotation will just be camera dot position now, and camera dot rotation. And then to use these functions, we're also gonna have to come up here and grab this type pointer include. Let's just paste it over here, and then we should be good with these controls at least. Over here we still have a couple issues. I think it's because we're just taking in the player rotation now as well. So let's grab that, and we'll just use, I mean, we don't actually have a rotation I think in here. I guess we'll just use 0, 0, 0 for the rotation in case it's a server-side cube, meaning another player. Okay, so if we launch this now, hopefully we're gonna see the ability to control the rotation of the cube. Okay, so there it is at that 45-degree angle. The rotation here seems incorrect though. It just seems to be tied to the position, so I must have messed that up. I did say camera rotation though, so that is a little bit weird. Where do we even set, yeah, we must be, yeah, player rotation. That's the camera position and the camera rotation. Right, okay, let's call this camera position and rotation, and then we'll also have the player position and rotation, which is going to be our player position and our player rotation. Now, with our player rotation, I think this is just in degrees, and then we eventually, yeah, we convert it to radians when it's time to actually build up our push constant buffer. So that should be fine. Okay, so now we've got many more controls. We've got our player position and rotation, which you can see works like that. Might also like just rotate this to like 30 degrees by default as well. So on the X over here, we'll come in and just say 30. And now we finally have the cube in more or less like a good place. Maybe one other thing I would do is just give it some like constant rotation. So I might take player rotation inside on update with our time step. And then we have player position over here, but let's come over here and just do player rotation dot Y. So I'm just gonna have it rotate along the Y axis plus equals maybe just like time step. That might be too slow actually if it's in degrees. Okay, so that doesn't even seem to be working for some reason. I see. It's because client layer on update does a little return if we're not connected. So we actually can't kind of play the game if that's the case. Let's just add a little and if false over here to disable this, and then we should still be able to move our cube, and then that rotation should happen. Okay, we get a little crash if we do that because the interface is null and we're trying to send a buffer. So let's just make sure that this part may be down here. What I'll do is I'll just come over here into our if statement, and then I'll put it down over here, and I might just say that if we are connected, we'll just go ahead and actually write that buffer and send it. Because obviously we can't send the buffer to the server if we're not connected to the server. And this will just still let us interact locally, which is what we're trying to do. All right, so we are rotating very, very slowly. So let me just up that a little bit. Okay, and now we have a nicely rotating cube, which is great. All right, finally, I feel like this was just like the setup for this video, which took a long time, but I'm trying to include everything, obviously. So hopefully that didn't take too long. Let's start talking about, I guess, the situation with the normals, right? So at the moment, we have a cube that does not have normals, meaning it does not know which way each face is facing. What we need to do is for each vertex of each triangle, we need to basically give it some information, some data that tells it which way it's facing. So in this case, this face, this triangle is facing that way, which is the positive x-axis. And obviously it's not going up and it's not going in this way. It's just facing in that way. Now, obviously we have to do this in terms of triangles because our cube is being rendered out of triangles. And this does mean that we need to introduce more vertices. If we have a look at what our current situation with our cube is, over here inside init buffers is where we actually set up our vertices. You can see we only have 8. And that makes sense if you just look at the cube and you just look at these 8 positions. So we have one over there, here, here, and here. That's 8 vertices, 8 unique vertex positions. Even though we have to draw so many faces and so many triangles, we have to draw 12 different triangles because each face is made up of 2 triangles, right? We got this one and this one here. A lot of the faces share vertex positions for some of their vertices. So this corner over here is shared by this face, which is two different triangles, right? This face, which is also two different triangles, but only one of them in this case touches that vertex, and then the face on the other side as well. That's why we only need 8. However, once we start thinking about not just the position of vertices, but where they actually point, which direction they're facing, then obviously, even though these triangles, this one, this one, this one. So we've got like 5 triangles in this case that all have this one singular vertex position that's the same. This face faces this way. These triangles both face that way. And these triangles both face this way. So that's 3 different unique normal vectors that we need for this one vertex. And so therefore we can't just have one copy of that vertex and be done with it. We need 3 different copies of that vertex. So in practice, this basically means that our 8 vertices are going to grow to 24 vertices. We don't quite need 36, which would be if every single triangle had its own unique vertex. That comes from those 6 faces containing 12 triangles, and then each triangle is made up of 3 different vertices, and that's how you get 36. We still don't really quite need that, because if you count it up, then every single vertex corner that we have over here, so every one of those 8, requires now 3 different directions to point in. And 8 times 3, of course, is 24. So how do we set this up practically now? Well, we can follow this guide. I think one thing that I had to change was the Z, right? So the Z we flipped. Instead of -1, it should be +1, but I didn't bother like redrawing this. So that just means that we just negate like the Z normal, but otherwise everything should be okay. So this is our 0 over here. So let's, I guess, start from here. That seems reasonable. So we have -0.5, -0.5, and +0.5 is what we should have. So there's that -0.5, -0.5, and +0.5. Let me just collapse this to make a little bit more room. So that's okay, but now these vertices are gonna not just contain a position, but also a normal. So usually when we start dealing with like a structure of multiple variables inside sort of one contiguous buffer, we like to introduce structs or some kind of like structured data type that isn't just a bunch of vec3s, because we could obviously just be like, okay, well, a normal is also a vec3, so let's just like double these, or in the case of having 24 unique vertices, we would be like, okay, we have 48 now, because we have 48 unique vec3s, where the first one is going to be a position, the second one's going to be a normal. That makes things unnecessarily messy. So instead what we're going to do is we're going to introduce the concept of a struct, and specifically I'm going to introduce it up here, and I'm going to call it a vertex, and then I'm going to give that vertex a position and a normal. So now we just have 2 vec3s, we have double the data stored per vertex, we have a position, and we have a normal. And now this is going to be just built out of vertices. Now, does this change the internal data layout at all, or what our memory actually looks like? No, absolutely not. It's identical. Obviously, now we have double the amount of vec3s for each one of these. So if I have 8, instead of having 8 vec3s, we have 16, because each element now has 2 of these vec3s. But if you were to look at this in memory, it's completely identical. Introducing a struct doesn't change anything, because obviously we're not making like a vertex pointer array or anything. It's just a vertex array. So it is literally just these 2 things. Now, how many did we say we need? 24 unique vertices, so I'll change it to that. How do we actually create these? Well, the easiest way, probably, I don't know, I'm thinking about how to make this look nicest in syntax, but if you just put curly brackets around the actual vec3, you're now basically making an instance of this vertex struct. You could also write vertex here if you wanted to. Sometimes compilers will want you to do that, just in case it's ambiguous what type it might be, but in this case, it's going to be fine, I'm sure. The first is going to just be the vertex, and the second one is going to be the normal. Now, be careful, because as this grows, like if you start adding texture coordinates, binormals, tangents, colors, whatever else you might have inside your vertices, obviously this is going to get very messy, but I would probably venture to say that by that point, you'd probably be reading in like model files, you know, from files. You wouldn't just be hard coding things like this unless you were specifically making some sort of like mesh factory, which generates meshes, or obviously procedural meshes. I think in that case, another thing you could do is you could just make like an array which had like 24 vertices like this, and then you could just be like, okay, this is my position, this is my normal. In fact, I don't know, maybe I'm a little bit tempted to do that, because it would just make this more readable. especially to beginners, which are somewhat the target audience. Beginner to intermediate people, probably the target audience of this series. So maybe let's do that instead. I should probably also not use just C-style arrays like that, but also switch to using standard arrays like this. If I have a look at how this is used though, it's not really going to matter too much. I think I'm just doing size of, which is fine. Whereas with arrays, I guess I would have to do vertex data.size times size of vertex. But anyway, we'll switch to this nonetheless. So let's go ahead and make this vertex data here. And then we're going to go through and we're going to set like all 24 of these vertices. This is probably the last time you're going to see me actually write out vertices by hand, because again, as I mentioned, at this stage, this is just getting a little bit messy and completely unnecessary. You would just make like a cube in Blender and then export it as like a GLTF probably these days, and then just import it. And you would use like an importer to just import it. And I think that's probably something we'll do. However, because this game is called Cubed, maybe we will never take in meshes from files. I don't know. We'll have to see. But anyway, I'm still going to show you how to do this by hand, but you normally wouldn't. That's all I'll say. Okay, so let's begin with the position, and we'll set the position to this. And then we're going to obviously have normal. And then the normal, as we saw over here, for this particular vertex is going to be 0, 0, and then positive 1. You can actually kind of tell which way it's facing by just looking at the fact that this is going to be constant for all 4 of these. So if we look at the first 4 positions, right, we have them be the same, whereas everything else changes. So that kind of tells us that it's going to be facing in the positive Z direction, right? It's all kind of 0.5 Z. That's the common denominator, if you will, of that set of vertices that make up that face. So now we're really going to do it in like a kind of a per face basis, and you need to be aware of what face we're on. So we're on this face, which I guess you would call the front face. We did call it front, which is nice. And then I might just align these so it's a little bit easier to read. And then the normal obviously is going to be, as I said, 0, 0, and then positive 1 over here. So 0, 0, and then positive 1. Let me again just align this. And then we're going to continue going through this as normal. See what I did there? So we'll go up here, we'll do negative 0.5, 0.5, and then positive 0.5 as well. So let's duplicate these. This will be number 1. Okay, so that's positive 0.5. And then the normal, as you can see, is going to be identical. So just the position changed there. Vertex number 3 over here, which is this one here. Going to be positive 0.5, positive 0.5, and positive 0.5. And then finally, we don't have to make up both of these triangles because both triangles face the same way. They both have that same normal. So we don't need to duplicate these vertices or anything like that. We can just go straight to vertex number 3 over here and just write that in. So for our last one, that would be positive 0.5, negative 0.5, positive 0.5, and obviously the normal is going to be the same for all of them. And that is our entire face. So now we just need to duplicate this for every single face. And I am definitely not going to show this full process because that would be, I think, unnecessary. So we're just going to fast forward like through this section as I do it. So one little hint, by the way, that might make this a little bit easier to work out because there's just a mess of numbers here, is you can actually refer to the indices you created as long as they obviously work. So we know that this face is made up of 0, 1, 2, and 3 out of these existing positions that we had, our alt positions. So the right face is made up of 3, 2, 5, 4. It means we use this one, 5, and 4. So basically these 3 are what we can just grab and paste into here. And in fact, you can drop this down like this so that you can always have a reference to your indices. So the right face will be number 3, which is this. So we know that's definitely the first position. Number 2 is next, which is this one here. Then 5, which is this one. And then 4, which is this one. So obviously they have to be unique. I think I may have screwed up the 5 one. Yeah, I did. So 5 is actually this one here. So let's go back and make sure 5 is here. So obviously just the unique indices are what we care about. 3, 2, 5, and 4. And then that's really all you need to do because we know that the normals are all going to be the same. So I've already set them to 1, 1, 1, 1, and that's it. And then that's really all there is to it. It's just rinse and repeat from here. You can see just how much data it is, just writing it out by hand. Again, do not advise doing this unless you're learning, I guess. Like, just make a cube in Blender, import it. Easy. It's all automated. Way less error prone than me. Like, I'm going to be very surprised if this worked with no mistakes. And probably half of my day today is going to be trying to figure out what's wrong here while that just gets cut from the final video. But anyway, let's have a look. So indices, though, is one other thing we're going to need. Now, here's the thing. The indices have obviously changed. However, they do follow a pattern. 0, 1, 2, 2, 3, 0. Literally all of them are going to follow that pattern now. We can see here that now that we have a per face situation and it's not made up of like duplicated vertices across different faces, like we're just drawing quads. We're just drawing like squares to make up the cube. So 0, 1, 2, 2, 3, 0, 4, 5, 6, 6, 7, 4, 8, 9, 10, 10, 11, 8. That's all it's going to be. So you could easily just like write a for loop that does this. I guess I probably will. So let's just make an array as well here. So we'll do 36 indices. That obviously doesn't change. We'll call this our indices. I'm going to go through probably on like a per face basis here. So we have 6 faces. So I'm just going to go through everything per face like that. And then we'll just do indices. Actually, since we're going to go through this per face, we'll still go through this 36 times, but we can set this to I plus equals 6. So it advances basically per face. And then here we can just do I plus 0, which is meaningless, but it will make everything else look nicer. We'll set this to like 0, for example, plus an offset, which is just going to advance by 4 every iteration of this loop. So we can do offset plus equals 4 at the end of this. And you'll kind of see how this works in a minute. So we need 6 of these, obviously. So I'll duplicate this 6 times. 1, 2, 3, 4, 5. And then obviously this is going to advance by 6 next time. So it will kind of keep going. This will be I plus 6, the next iteration of the for loop. And then this is going to be 0, 1, 2, 2, 3, 0. But it's going to be plus offset, which means that next iteration will be 4, 5, 6, 6, 7, 4, right? And that's all there is to it. You can write it out by hand if you want. Obviously, that would just be like 4, 5, 6, 6, 7, 4. This is probably a bit less error prone. I don't know. Just either way is fine. You can see it basically ended up being the same amount of code, and you lose your designations, and it's probably more complex. So I don't know. You do you. You know what? This is actually going to be useful in case you have like a batch renderer or something that renders cubes, I guess, or quads, and you would change this a little bit, because that way you could fill an index buffer with indices and you could have like 100,000 of them. And obviously for that, you wouldn't write them out by hand. You would use like a for loop. So maybe that's helpful in that case. Okay, awesome. So we have to change this a little bit though. So now the size of vertex buffer is not quite right. It's going to be vertex buffer, vertex data dot size times the size of each individual vertex, because we still need this in bytes. Now, this probably is going to want, okay, good, a uint64t, because size is going to be a size t, which is a uint64t. So I'm just trying to make sure that I'm correct there. And then when we actually give the data, we need to do dot data. And Visual Assist is trying to change my dots into arrows annoyingly, but we're going to make it not do that. So the size is going to be this as well. To be honest, you probably could use size of, because it's a stack array. I think you could probably keep. I've never tried that, to be completely honest with you. But if you look at what an array is actually made up of, because the size is not a member variable, the size is just the actual template variable, which, you know, this template argument is 24, which means that this return size is actually kind of hard coded to return 24. So it's not actually storing size as a member. So all it's actually storing is a stack array that is exactly that. So to be honest, I think you could use just size of that like stack variable directly, and that would actually give you the correct size in bytes. But nevertheless, I'll show something a bit more extensible, because if you had a vector instead of an array, that wouldn't work. So we'll do indices.size times size of uint32t. And then obviously with the vertex data size, we'll have to put that in here as well. And then the index data size, we will also put that in like this, and this will be indices.data. Okay, I think that's it. I think that's correct. It's been C++, because we were using C-style arrays before, which are totally fine, but this might be nicer. I don't know, depending on who you are as a person. Now, if we try and run this right now, I suspect we might get a crash. I don't know if we'll get a crash. Yeah, we won't get a crash, but we'll get something like super weird going on. The reason why this is happening is because the way that we set up our actual pipeline, which defines like the vertex attribute layout and just the layout of our vertex buffer, obviously now no longer matches the data, the actual buffer. Because what we've done is we used to just have position, 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 position. It was easy to render. Now it's interleaved with normals. So we need to make sure that it's aware that our pipeline and our shaders and everything are aware that we have like a position every 12 bytes instead of ever like packed together tightly. That doesn't necessarily mean we need to introduce normals and start using normals immediately, but it doesn't mean we have to modify our pipeline to just be aware of this, right? So the stride here really is just going to change to being 2 vec3s, or, and I meant to write this outside like that, or just the size of a vertex, right? So that's basically the big difference. I think that if we just tried that, that should probably work. without even telling it about normals in there. And there you go, right? So we get the same result, and it has in fact worked, no difference whatsoever. So we don't even need to add the concept of normals or be like, hey, there's additional data in that buffer. It doesn't care that there's additional data in the buffer. All it cares is you've got that attribute. Where is it? What's the stride? Meaning how many bytes are there between each unique vertex inside that buffer of just memory. Because remember, it's just seeing a bunch of bytes. It needs to know how to actually like read the data that's important to you. And the reason why I say the data that's important to you is because if we have a look at our shader is specifically interested in a position, and that obviously determines that attribute, that vec3 determines where that vertex gets drawn inside our window. So it's very important that we still have access to this. Now, let's introduce these normals. So how do we do that? We're going to make another attribute called normal. It's going to be in location 1. And it's still going to be a vec3, obviously, same type. And that is it from the shader side. We can now start using that. And then over here inside our vertex input attribute description, we just need to basically specify that there are now 2 attributes. The first one is still going to obviously be that position. I might just mark it as position. And then this is now going to be our normal. So this is obviously going to be index 1 inside this array. Location is going to be 1. Format is all exactly the same binding, same offset, same everything, just location 1. Now, if we follow this attribute description down here, you can see that obviously we set the description count to the array size. So we actually don't need to change anything here. And now if I run this, again, we're just making sure that we get the same result. Nothing's messed up. It does look the same. That's good. And we don't get any Vulkan validation errors, which is also nice. So let's try actually using the data to make sure that it worked. So instead of outputting our color as this, like one of these colors over here based on the vertex index, I'm instead going to set our color to just be normal. And I'm just going to set it like this. It's a vec3 out color. So let's just see what this gives us. Okay, nothing, because obviously we have to compile our shaders. Let's go ahead and go to this directory, double click on compile, and then let's run this. And there we go. So we get some data here. This is probably wrong. So you can see that we do have a bunch of like normal-ish data, but this is wrong. And this is why it's so important, by the way, to visualize your data using colors. So this is like a really, really important skill to just be able to output data as colors and then obviously crucially be able to read that. So I can see that this is wrong because what would we have expected? Well, every single face has the exact same normal, which means that this entire face should be red. Right? We should just see a constant red across this entire face, a constant blue across this face, except it should actually be black because it's -1 instead of +1. We flip them, remember? And then this face over here should just be green, right? Because we have 0 in red, 0 in blue, and 1 in green. So even though I was expecting myself to mess up here, but it's probably good that I did because you can see that this gives me an opportunity to talk about how important it is to actually be able to kind of debug colors. So that's another skill that you should definitely practice. So why are these not constant? Well, it probably means that this vertex is probably facing that way, so it's blue, but they're all supposed to be green, and they're not all green, and the way we've made up our triangles is probably wrong. So now I'm gonna go ahead and debug this. And by debug this, I literally mean I'm gonna have to proofread like all of this. So wish me luck. Before I actually start proofreading everything, I just wanna make sure that this offset, I think this is wrong. I think this is supposed to be 12 because it's probably the offset in bytes. I thought it was some other offset. When you are unsure, it's important to consult the documentation. So the offset is a byte offset of this attribute relative to the side of the element in the vertex input binding. Yes. So it's basically the offset. I don't know how I forgot that, but it's basically the offset within this struct. So our stride is like the entire vertex. That's each element. That's each actual vertex. So where is this located from the beginning? The reason why I maybe didn't think about it is because since we specify the format here, we obviously know like how many bytes it is. So therefore, why would it not know the offset? But there are different semantics at play here because the format doesn't actually have to match the byte offset anyway. It's a little bit complicated, but this should in fact be 12. Now, what's a better way of us actually doing this? There's something called offset of, which is kind of like a macro that's built into this. We can actually just specify vertex as the type and then which member within vertex we're interested in. So normal. And we can do the same thing for here, even though it's going to be 0 anyway, and just specify position. Now this I think will give us probably not the right data type. So we should cast this into a uint32t. An offset of is a very clever little macro. If you have a look at what it does, all it does is it tries to just find the memory offset of a member from 0. So obviously if you create a pointer at 0, it's kind of like a null pointer, but again, we're not actually reading or writing data, so it doesn't matter whatsoever. We're just seeing that if this was a pointer and we went to this member and we got the memory address of it, then where relative to 0 would we be? If it's a second vec3, then obviously the answer would be 12, which is exactly what we're looking for. But this obviously makes the code look cleaner, and in case you rearrange your struct or do anything else, it would also make it look better. So hopefully I didn't make a mistake. Hey, let's go. I'm actually really excited about this because I was not looking forward to going through all of that data. This is exactly what we would expect. Let me just advance this a little bit forward. And then you can see we've got 3 different colors. We've got green, blue, and red, as you would expect. However, the other side is black. And this is where a little bit more of that kind of color debugging skills comes into play, and why I think it's very important as well. The reason why is because obviously a lot of these numbers are negative. So if we have a look at this actual vertex data that we have here, we have a lot of normals that are like 0, 0, -1. Right? So that's just going to get clipped to 0. That might as well be 0 in the blue channel, and obviously 0, 0, 0 gives us black. So is there anything that we can do to maybe just be able to see all the colors? Because really what I'm looking for is to make sure that we have unique colors on each face and that they're constant, they're consistent across that entire face. Well, what we could do is basically like remap this range. So what is the current range? Well, we know it's from -1 to 1. That's the entire like bandwidth, that's the entire range of our normals. So if they're from -1 to 1 and we can only see colors from 0 to 1, then what can we do to this to make it equal to this range? Well, we can simply multiply this by 0.5 and then add 0.5, right? Because what that will do is that will change this to be -0.5 to +0.5 because we multiplied it by 0.5. I could not have picked a better place to draw on, but you'll have to just bear with me here. And then finally, adding 0.5 obviously means that our -0.5 to 0.5 range, we add 0.5, so now it's 0 to 1. So over here, when we set our output color to be normal, I'm just going to multiply it by 0.5 and add 0.5. Let's go ahead and recompile our shaders, which probably make this like a build step inside this or something, and there we go, we finally see something. Now, is it fantastic? Well, no, but obviously it should give us a pretty good visualization of all of these colors, and you can see that we see different colors. Now, one thing that it's done, potentially inadvertently, is obviously like, if we had red, which used to be 1, 0, 0, it hasn't just kept it as that, it's actually made it 1.5.5, right? So that's why that red now looks way more faded, because it's not like full red anymore. But again, the point of this is just to be able to see, okay, we do in fact have normals and they are working correctly, which is great. Let's actually use these normals a little bit for something. And I'm gonna keep this very, very simple for now, of course, because that's definitely not the point of this video. But what I wanna do with these normals is actually output them. So instead of out color, I mean, we can have out color, but I'm gonna add an out normal, making sure that we put that in location 1, and then inside our fragment shader, we'll take in the normal at location 1. I really should have this output as like the first thing here, because that's the most important thing of this entire shader. Let's go back to in normal. Out color we can maybe keep as that, but out normal, I'm gonna set obviously to that unadulterated normal, just the normal that hasn't been kind of like scale biased here, multiplied by 0.5 and added 0.5 to be in that range, because we want the negative numbers for what we're about to do. And then with this in normal, what I'm gonna do is basically, I'm just gonna stick a light somewhere, have like a little light direction. So we'll have a light coming like, I don't know, 0.5, 0.5, and 0. I mean, to be honest, I might as well just write it as 1, 1, 0, and then we're gonna normalize it. So we have a light direction. We have a normal of that particular face. So now what we can do is we can just compare that normal to that light direction to basically set the intensity of that light. So that's just going to be the dot product between the normal and the light direction. That's basically already going to give us an intensifier. I'm going to make sure that this doesn't go below 0 though, because it obviously can depending on that angle. And then the other thing to just take note is like what direction you're kind of playing with here. Now I've written this in a way that makes sense. However, the normal, right, points this way. And in this case, the light direction, I've written it as like, it's going to basically kind of be pointing that way, right? So if you had done the light coming down, which would have been like -1 for the Y, then it would potentially like make sense to basically negate that vector, because you want the vectors facing the same way when you compare them with a dot product. If you have an inbound vector like this compared with a vector like that, then really what you're comparing are these two vectors, which is not something you want to do. Now, this is definitely not a math lesson, but the dot product will basically give us a result that is going to be dependent on the relation between two different vectors that we give it. And this result is going to basically be like a cosine. So it's going to be between 1 and -1, where 1 would be they're just the same. A value between 0 and 1 means that it's an acute angle, so it's less than 90 degrees. 90 degrees exactly is going to give you 0, and anything past that is going to give you a negative number. And you can see why this is useful for lighting, because basically we're trying to see how much does that face the light. If it's facing the light, then great, fantastic, intensity plus. If it's facing away from the light, so it's probably like above 90 degrees, the light's coming in this way and it's facing away from it, then obviously it's not lit directly by that light. This will just give us kind of like an intensity value, and then we can just show, like, just immediately just display that. Obviously this is going to be kind of colorless here. Let's recompile our shaders. And you can see we get mostly black here, but it is in fact coming from the top, which is good. But then as we rotate this, you can see some of these sides are going to be a little bit lit. Some of them are not going to be lit. Now, generally you could add a little bit of ambient light by maybe making this like 0.15 or something. Okay, so now we have like a little bit of lighting here, but then as we kind of rotate this, you can see that some faces are lit, some faces are not lit. And then you should hopefully be already seeing a problem with what we've done here. And that is that no matter how I rotate the cube, it kind of looks like the light is painted on, right? So now it's just all black. And the reason why is because these normals completely have no effect with the actual transform of the cube. So the normals are kind of rotating with the cube, whereas that obviously is wrong. And the way we fix that is we just make sure that we actually take into account this transform when it comes to these normals. So instead of just a normal like this, we grab the transform and we need to multiply it with a normal. But wait, stop, that's wrong, because the transform doesn't just contain it contains three things, right? It contains the translation, it contains the rotation, and it contains the scale. Now, which one of these are we interested in when it comes to manipulating our normals? Just this one, just the rotation. We don't need the scale and we don't need the translation. If we have the translation, that wouldn't make any sense because our 1, 0, 0 normal that's facing this way would suddenly get translated. So it might be like 3, 2, -1 or something. Like it's just going to change completely. We just want to rotate it potentially to suit the rotation of our actual object in world space. So it's very easy for us to just get rid of the transform. We just need to make this a mat 3 instead. And in fact, it's not even going to let us multiply a mat 4 with a vec 3 because they're different types. A mat 3, however, with a vec 3 will in fact work. So that's good. I don't know why it's saying it's ambiguous, but that actually should work. Now, scale is another thing we haven't addressed yet, but I just want to make sure that this works first. Okay, so now you can see as this rotates, we can kind of see how this face is suddenly getting lit, right? And then if I rotate this and show like another side, well, the light is basically in a constant direction because the normals are changing. And it looks obviously a lot better than as if the light was just painted on. And as we rotate the cube, that doesn't make any sense, right? So this is important. The problem with this though, is that we still have scale. Right? We still have scale in the sense that if the scale right now is 1, but if we have a normal that's 1, 0, 0, and then we still have the scale in this matrix, then if the scale of the cube is 2, then, well, we're going to scale that normal up as well. And we need our normals to be normalized. So there's the hint. We can just normalize this. So once we do that transform over there to apply the rotation, we can just basically normalize our normal and make sure that it is in fact still a unit vector. One final thing that I want to mention about this, which is probably getting a little bit too deep here, but it actually, I think it will affect us if we make everything out of cubes, and that is non-uniform scaling, right? So this is a nice kind of easy way to do this. However, the problem with this is that if you have the cube non-uniformly scaled, then obviously when you apply this transformation with the scale to the normal, even if you do normalize it, it's still kind of skewed the normal to a bad place. So usually what you would do to avoid that is you would use the transpose inverse of the matrix, which sounds like a lot, and it is, but if you just do transpose inverse and then this entire matrix, and then you multiply it with that normal, and then like we're normalizing it afterwards, you may also have to normalize in the fragment shader or the pixel shader because sometimes I think there can be some interpolation issues. That should look exactly the same in this case, but in case you had like a mesh that was not uniformly scaled, then this would in fact look correct because it's basically getting rid of that scaling entirely. Cool. So that's pretty good. What we can do if we really wanted a color is that in color that is currently actually set to our normal, we could also multiply that with the intensity instead. And then that would basically give us like some color. And you can see that the face that is facing the light will also be lit. I think what we'll do in the future is we'll just have different cubes. And actually, maybe if I lower this a little bit, it'll just be a little higher, that light. What can I say? I'm an artist at heart. I want this to look good. All right. So there we go. We've got our cube. We've got some lighting, which means our normals are obviously working. So that's basically the conclusion of this first part of the video. Now we're going to go ahead and talk about descriptors, and basically our goal here is going to be to make this be a textured cube. So that's the ultimate goal. Probably going to take a little bit of time, especially because we need a way to actually read the texture and then upload it, and then there's a bunch of stuff to do, but I would like these faces to be textured. So brace yourselves, because this is going to be a little bit challenging. So the first thing that I think I want to look at is basically the documentation, because I don't exactly remember how to do this. I think I could probably do this, but in the interest of like you guys, I don't really want to do that. So there's a texture loading sample, which seems to demonstrate a whole bunch of different things here. There's a staging versus a non-staging buffer. IMGUI also does that. So remember we were using like IMGUI as an actual source. If we have a look at the Vulkan implementation for this is obviously going to do some texture things. So you can see it creates a descriptor set over here. That's for an external texture, but I think for its own fonts and stuff like that, it needs to actually create a texture. So create fonts texture. You can see it's going to create an image, allocate some memory, create an image for it, create an image view. It's going to need a sampler as well. In this case, it's actually creating an upload buffer, which is going to be our staging buffer. And then it's going to upload to that buffer. And then it's going to copy it to an image, which is where that staging thing comes in. And that's pretty much it. So you can see, I say that's pretty much it, but you can see it's moderately complicated. We could base it on this. I don't know if there's any advantage to basing it off of this. Probably not. I think it does basically exactly the same. So you can see it's going to do command copy buffer to image, and then we're going to do that same thing here. So I think since we've already got this in Visual Studio, we'll just do this. The first thing that I want to do is I'm going to just generate a texture. So instead of actually loading a texture from disk, I want to just like create a texture basically in C++. Just set it to like alternating pixel colors or whatever. Maybe set it to just like a solid color like pink to begin with, just to see if we can get that data onto the GPU. So that way we're breaking down the task into two different things instead of trying to go through the process of loading an image and then making sure that that's like in the right pixel format, in the right color format, and then being like, oh, why doesn't it work properly when applied to something, you know, in Vulkan or whatever. I'm just going to take that part out of it by just generating a texture. I think what I'm going to do is just copy like this entire function. Lots of copying. And then over here inside our cubed client, inside the renderer, and then we're also going to make a texture.h. And then we have probably had like a cubed namespace, right? Class texture. Okay, so this is really interesting because we're actually introducing resources now, and resources have to have lifetimes. And you know, in Hazel, this would be a ref counted object. So we use reference counting, intrusive reference counting in Hazel to basically make sure that objects, like their lifetime is correctly controlled. And that's very important, especially if you have multiple threads, because you don't quite know who's going to finish with the object last. And obviously you want it to stay alive until it's definitely no longer needed by like any thread. So that's where intrusive reference counting is amazing. You could use shared pointers for this, but that comes with some limitations unless you also use the intrusive variant of those. We're not going to talk too much about lifetime. I think we're just going to like just get this running as usual. So let's go ahead and probably we've got the buffer struct here. So let's just include buffer, which is probably like, where is that located? Walnut core buffer. So we'll include buffer, and then we're just going to take in like some texture data like that. I'm probably going to make an init function as well for it. Let's include texture, namespace, cubed. And then we're going to come over here and we're just going to create all of these. Okay, so init is where I'm going to paste everything. If we go to our renderer, we can have a look quickly at maybe the kind of stuff we'll need. So we obviously want Vulkan. Yeah, Vulkan.h. I'll just grab Vulkan.h for now. And I'm going to put it up here. We're going to need some IMGUI as well to get like the backend data, which was that needed for? Yeah, the Vulkan init info. Okay, init. I'm just going to probably pass that into here, and then this will really just call init with data. Just don't really want to do it in the constructor here. Okay. So, yeah, let's get the Vulkan data. So we were probably doing that somewhere in the renderer, right? Oh, we weren't. Okay, so why do we need that exactly for init info v? And what does that get us? Yeah, the device, the allocator. We're not really using an allocator. Okay, I think that we probably don't need that. So if we look at renderer, we're obviously getting the device some other way, and it's just by get Vulkan info. Also, get Vulkan info is that init info. Yeah, so we don't need this because we can just do get Vulkan info, right? And that gets us this, which is great. I think the only thing we really need from there though is that device. So maybe we can just do like this. Not gonna worry about this, which is just getting the texture data for that particular font. Okay, width and height is important. Now, I guess if we're taking in a data like this, we probably want to also take in a width and height. Make a little section here for our member variables. Okay, width and height. And then we're going to go ahead and assign them in the destructor. Okay, create image. And then we need a place to store the image. So VK image image. So this is going to be our image handler from Vulkan. We're also going to need something called an image view and a sampler, which I'll just create all three of them here. This together basically makes up like our, well, minus the image actually, I think, makes up our descriptor info. There's also one more thing in there, and it's just VK sampler. So I'm just going to make all three because I know we're going to need all of them. So image view, image, and sampler. Image is like the actual image. A view into the image just means like what portion of it you're using, and you're going to need that for actually rendering. Okay, let's have a look here. So yeah, so this will be our image. So you can see it's pretty easy to just make an image in Vulkan. This is just how we make an image. A lot of these are kind of important. I don't want to discuss this too much right now. So the format obviously is very important. So this just means it's going to be like an RGBA 8, like normal kind of RGBA image. Width and height, obviously, is the size of the image. That's important. Now the MIP levels, we're just going to set this to 1. So if you would have MIPs, you'd set this to something else. Unlike something like OpenGL, Vulkan will not generate MIPs for you. You have to do that entirely yourself. We might cover that in the future because obviously MIPs are very important, but you literally have to write like a whole bunch of code to just generate MIPs. And in something like DirectX 12, you would even do that by writing a compute shader or something that actually downsamples and creates these MIPs. It's a bit easier in Vulkan because there's a command called blit, whereas DirectX 12 doesn't have that. But anyway, getting a little bit ahead of ourselves, let's just go ahead and continue on with creating the image. Note there's no data in the image at the moment. We actually have to like allocate some memory for it and bind that image memory, and then that will be the memory behind this image. Check a VK result. We should have something like that inside here. So we have a VK check. So we're going to make sure that basically we don't create that error variable, and instead we just wrap all of the things that can return a VK result that we care about into VK check using VK allocate memory here. Usually, again, with Vulkan, you'd use something like VMA, Vulkan Memory Allocator. I think NVIDIA has something as well because that's AMD, but you can use it with any GPU, doesn't matter. It just does some Vulkan things. It's just a library. Because like Vulkan with allocations can get a little bit, I think you can only allocate like memory 4096 times or something. I don't know if that's still true, but anyway, I really do. Yeah, I've kind of forgotten the exact details. Usually Vulkan applications are expected to manage their own memory and basically, you know, do sub allocations themselves within larger allocated buffers. And that's where something like VMA, Vulkan Memory Allocator, can definitely come in handy. So we might switch to that as well in the future. Let me know if you want to see that in the comments below. Again, for a game like this simple, it might not be strictly necessary, but it's definitely nice to have. Okay, so this memory index, remember we had over here. So I think what I might do is let's just grab this function and let's expose it. I'll make a little public static section here, and we'll have this, maybe I'll just call it get Vulkan memory type. We'll take that in, and that way we can just do renderer get Vulkan memory type. We will include the renderer. Okay, so lots of stuff here that we need to obviously replace. So device, VAllocator. I might just, so VAllocator will just replace with null pointer. So what I've done here is just doing a find replace, Alt A, that's replaced all of that. And then I think we also had VDevice, which I'm just gonna replace with device. And that will just help us a little bit. So font image over here and font memory are two different things. Oh yeah, we also need the memory. So this gives us a VK device memory, which I'm going to have to store as well. So VK device memory. So that's going to be our memory, and that's going to be our image. Okay, cool. No more errors. Looks nice. So that's the whole image situation. Now the image view. So we're just basically creating like a way to use this image. That's really all there is. It's very, very simple. It says like how many MIPs we want to look at, what layers we want to look at, like what type it is, what format, that kind of stuff. Really simple. This is necessary because sometimes you might want to like write to only a particular MIP of a particular image or something, and this lets you do stuff like that. And then we'll change this to be image view. Now this is actually creating a descriptor set, which we don't need to do. You can see it's not actually used anywhere apart from at the very end. Descriptor sets we'll talk about a little bit after we actually get these images up and running. So I'm just going to get rid of that. Now the upload buffer is going to be important. What is upload size? Because didn't really see that. Okay, upload size was this. So let's grab this from that other function, and we'll talk about that a little bit here as well. I'll put it up here at the top. So width times height times 4 times size of char. So basically for this particular format, we need to calculate how much data we actually have in the image. So it's usually going to be width times height. That gives you the number of pixels. And then how many bytes do you have per pixel? So for an RGBA8, we have 8 bits per channel, 4 channels. So that's where the 4 comes from, 4 bytes per pixel. This is unnecessary in our case because that's just going to be 1 byte. So I'm just going to get rid of that, and then we'll just be width times height times 4. Now you should absolutely look at the format that you're creating. This is simple, obviously, at this point in time. So therefore I'm not really caring about that. But like in something like Hazel, you know, we would not just create a texture with not even specifying a format. You'd absolutely specify a format. And then you would know based on the width and height, if you're actually uploading data and you want that texture to be appropriately sized, you would be like, okay, my format is this. These are the dimensions, like how many bytes does that occupy? And then that's what you would use instead. I'm just gonna rename this to size, and then we're gonna use size over here for everything, as you can see. So that's creating the upload buffer. So the upload buffer, so this is just going to be like a staging buffer that we use. We probably don't need to store it unless we're going to reuse it. So let's do VK buffer staging buffer. I'll call it a staging buffer rather than upload buffer because that's a bit more common. So we'll have a staging buffer, and then we'll check to make sure that we created that successfully. Usually you'd also have like some utility functions to just create temporary buffers for you, or have a pool of them that you can reuse or whatever. They do have to be appropriately sized, obviously. Usages we haven't touched too much on, but you can see that when we created our image, we had the usage marked as sampled because we want to read it from like a fragment shader and sample it, but then also transfer destination bit. So that just means that we're planning to transfer data using like our GPU's transfer queue from like a particular buffer into this. So this is the destination for a transfer. And then you can see from our staging buffer, it's going to be the source of a transfer. So that's important to note as well. Okay, so there's that memory type index, which I'll replace with renderer and get Vulkan memory type. We'll also create a VK device memory, which will be our staging buffer memory. And that's what we'll use here. Then we'll bind the buffer with some memory. Again, not going to worry too much about alignment over here. Probably going to regret that later, but it's just what I'm doing for now. Surround these with VK checks. That looks pretty good. Now we'll upload to buffer. So we need to check, we have our buffer over here. We just want to upload it basically. So it's going to map memory in order to do that, which is fine. So here's our staging buffer memory that we are now mapping so that we can mem copy into it. So this is the mapped memory over here. This can be any type you want. Usually I use UN8Ts instead of chars because they're actually guaranteed to be that size, unlike before when we were doing size of char because we didn't know. And then pixels is just going to be our buffer data, which we actually called data. So that's our parameter that we're taking in over here. So with the size, you can see that it's using our size that's here. We kind of expect, you know, that size is going to be equal to data size. If it's not, then I guess I'm going to put a breakpoint here basically and probably return without doing this because that's a bit weird. We should definitely make sure that we're setting the right thing here. Otherwise, it's probably not going to give us the result we want. So that's a good little check. Usually I just assert or something like that there. Okay, memory is going to be the staging buffer memory. And I'm just going to replace this stuff first, and then I'm just going to check to make sure that everything is correct. Okay, so this is obviously very simple. I might just make this a little bit more simple even, because we've only got one of these. Yeah, pretty simple. Like the only thing we're really doing is reading from that buffer data and mem copying it into our mapped memory that we're then going to flush, which is then going to basically get that memory into the staging buffer memory. Just like we did with like our Vertex buffer, we need to copy it from that staging buffer into our actual final image memory, which is what's going on over here. So this stuff is, again, because it's already written for us, it's very, very easy. Otherwise, you can see that this would have probably taken a little bit of time to actually write out yourself. But I'm GUI to the rescue. So upload buffer is staging buffer. Font image is just our regular M image. Region, obviously we want to make sure we're copying that whole region. This is just M image. And then descriptor sets we won't worry about for now. Command pipeline barrier to just make sure that that happens before we actually start reading it from the fragment shader. So we need to make sure we've finished uploading and transferring our image before we start actually trying to render with it inside the fragment shader, if that is the place that you're going to use it. Again, sometimes you might want to use it in a compute shader, in which case this would need to change. But anyway, that's complicated Vulkan stuff. I'm almost beginning to think that maybe, I know you guys wanted like a Vulkan series, but I'm almost like, is this just too much? Because this is why I didn't want to do a Vulkan series for so many years as well, because it's just like not something that I think makes for good YouTube content, to be quite frank, or any video content. It's something that you like actually start using, and then you have the documentation open, then you trial and error, and then you make sure everything's working, you keep reading stuff, you keep validating stuff. Like, it's not really, yeah. So let me know how this Vulkan stuff is going. But otherwise, like, I'm very, very, very seriously considering switching to NVRHI, which does a lot of this stuff for you, way less verbose, and it has multiple backends, so not just Vulkan, but also DirectX 11 and DirectX 12, and everything would be much cleaner and like automatic resource tracking and other stuff that make it easier. So, but yeah, let me know what you think. Okay, so we need a command buffer to do all this stuff, which I don't think we actually had here. So if we go back to our renderer, where we probably buffers, okay, create or resize buffer. Oh, hang on, did we not use staging buffers for this stuff? This we're gonna have to change to get. Oh, we didn't use staging buffers for this. Okay, so that's interesting because I definitely thought we were using staging buffers for this. So I explained it though. I think I explained it, but we didn't use it. It's just because it happens to be used in this example, I just went with it. But I guess I should elaborate here a little bit since this is the case. So we didn't actually have to do things this way. Although for an image, maybe it's mandatory for an image, but I don't see why it would be. So you can see that when we actually created the memory for the image. So this is us creating the actual image, which is the thing that has all the data. And then you can see that we got the memory type of device local bit. Now device refers to the GPU, right? And local obviously means it's local to the GPU. So this is not memory that's accessible by the CPU at all. When we did the same thing over here inside create or resize buffer, you can see we got a different memory type, a host visible bit. Host is the CPU. It's this C++ code. If we had just done that here, then we could have just mapped that memory and then put all the data there. But instead, we made this device local, and then that obviously means that we can't map it and set data from our CPU. So what we need to do instead is create a new buffer that isn't device local. So you can see our staging buffer is host visible, meaning it's visible by our CPU. We can read and write to it, upload our image data there, and then tell Vulkan, kind of GPU side, to actually copy that staging buffer to our GPU only buffer, which is our image buffer. Now, why was this done this way inside IMGUI? Well, it makes sense if you think about it, because these buffers over here, remember, what are they used for? They're used for actually drawing the UI. The UI is reactive. It changes like every frame potentially. We constantly need to keep writing data into that vertex and index buffer, probably not the index buffer, but into the vertex buffer from our CPU, like every frame. However, this image was used for fonts, right? This is like you load a font, you upload the glyphs, you're done. That's never ever going to be touched again. It's just going to be read from on the GPU. So you want that to be as fast as possible. Therefore, GPU only makes sense. But for something that's going to actually be populated and like written to very frequently from the CPU, that wouldn't really make sense. So that's why, but it's totally okay because this is definitely what you would do for like static textures, for non-like dynamic textures, meaning we're not updating the data every frame or anything or frequently from the CPU. However, the only problem with this it's not really a problem, but what we need to do in order to actually perform this transfer operation to get it from the staging buffer into our persistent like GPU only buffer is we need to actually run these commands. And to run these commands on the GPU, we need to create a command buffer and then execute that command buffer. Now, up until now, the way that we've been using command buffers, so like for example inside render cube, is we just have a command buffer that is our active command buffer and that's it. That's fine. However, we generally wouldn't do that for something like a texture because we don't just want this to go with the flow of our frame. We need it to actually happen like as soon as possible usually, or at least get queued up for future execution on something called the transfer queue. Now, I believe Walnut, because this is Walnut, I believe Walnut actually has its own image class that I've just realized that actually does basically everything we've done. So we didn't even have to take inspiration or like use IMGUI as a guide. We could have just used Walnut, the code that I wrote, as a guide, but I completely forgot about it. You can see it basically does the exact same thing we've done. We've got our like staging buffer here and everything, except the difference is going to be that you can see there's an application flush command buffer, and this command buffer, we do application get command buffer, and true just means that it begins it, I think, automatically. So basically inside the application class, inside of Walnut, we already have a way to obtain a command buffer, and basically a new one from a pool, and then add a bunch of commands to it, and then execute it. So that's how this works. So if we go back to our texture class that we just made, when it comes time to copy the image, I'm going to write application get command buffer. So not get active command buffer, but just get command buffer. Probably have to include application, which is in Walnut. And then it's going to be Walnut application get command buffer, which I think just gives us like a VK command buffer. So that's this over here. And then we need to call flush command buffer. So into that command buffer, we're going to put, obviously, we're going to encode all of these commands. And then at the end of it, we're just going to do Walnut application flush command buffer. And it's going to be that command buffer. And that's it. So that should get our image into like the right memory and everything. At this point, you'd probably delete your staging buffer because we made it locally, right? So this is a local variable. It's clearly not made for reuse. So at this point, we would just delete it. If we look at image just to see how to delete things. So this is our Walnut image. You can see that inside the destructor, we have this release function, which we probably should also have there. And you can see that it's going to do destroy buffer and free memory for our staging buffer. So if we just copy that, once we flush it, I'm just going to make sure that that's even got the same variable names, which is great. So we're just going to destroy our buffer and free our memory, and that's it. Okay, so clearly we also need to do the same thing with our texture in the destructor. I'm not going to complicate things by talking about this like submit resource free or anything for now. So this is clearly what we need to do. And we need the device as well. So let's grab that. And then for now in the destructor, just like that, I'm just going to paste this in. I guess we can do Walnut application get device, or I don't know if it shouldn't be any different from just get Vulkan info device. So, and then obviously our sampler, our image view, our image, and our memory. And that's it. We've freed everything, hopefully, when the texture gets destroyed. The only problem with this is, again, multiple threads, but also the GPU might still be using the texture, even if we have released it from the CPU. So therefore, you don't want to run this code until later, which is why this has a submit resource free to basically defer it. And depending on how many frames you have in flight, things get complicated, but for now, we're not going to talk about that. Awesome. We've got that going on. Now, how do we actually create one of these and use it? I guess we'll do it in renderer. Let's include this texture class that we just created. I'm going to probably just make it as a shared pointer for now. The reason why is because it is a resource, so we don't want to copy it ever, and we also don't want to delete it until we're definitely sure no one's using it. So we'll just make a texture like that, and then inside init, I'll just do it here. I'll just do texture std make shared texture. Okay, width and height, let's make it like 8 by 8. And then we're gonna obviously take in our texture data, which we're about to generate. You know, in fact, let's make it 1 by 1. So it's a 1 by 1 pixel texture, one color, right? And then that way, what we can do is we can actually just make a UN32T called color, set it to something like magenta, like this, and then pass that in as our buffer. So we'll just do buffer, color, size of UINT32T, and it's a walnut buffer. Texture made. Let's just run this and see if we get any like Vulkan validation issues. Okay, we do. Access violation, reading location that. So what is the problem? The range or the staging buffer memory size is 4. That seems wrong. Oh no, size is correct. 4 bytes. Ah, okay. I think I know what's happened. So one thing we did was this, remember, wasn't exactly like this in IMGUI. I think it was an array. And what I crucially should have noticed is that it was initialized, whereas we left it uninitialized. And since we left it uninitialized, you can see that the next is incorrect. So that's the one thing we didn't set. Every other variable inside that struct is set, except for this. And so it's just uninitialized memory. I think that's probably what's causing the issue because it's not exactly 0. If we try again with that set, then you can see that now next is in fact 0 and everything's initialized properly. And that should mean that this works. So very kind of hard to notice bug there, but make sure that you initialize variables or you set everything correctly there. Okay, so I mean, we don't have anything in our console, so I think that probably worked. So the next step here is going to be to actually use descriptors as a way to basically allow us to access that texture data inside our shader, because that's where we obviously need to read it so that we can actually do something with it. As far as descriptors go, basically all you need to know is that they are like a little bit of memory that's stored on your GPU, which tells you what/where a particular resource on your GPU is. So think of it almost like a pointer to a resource. More of a handle, obviously. It just identifies a resource. And a resource could be like an image, a texture. It could be a storage buffer. It could be a uniform buffer. It could be a ray tracing acceleration structure, etc. The documentation has a whole page over here, docs.vulkan.org, called resource descriptors. That goes into a lot more detail as to how they work and what exactly they are and how to use them. I think descriptors are probably one of the scariest things about Vulkan, especially in the very, very beginning. But then once you understand how they work and what they actually do and why we even need them, they become very, very simple. I think it's further complicated because there's the concept of descriptor sets, and you can actually kind of sort your descriptors into various sets. So descriptors are grouped together into descriptor set objects, and that can complicate things, certainly. I don't really know how complicated we're gonna get as far as this game goes. So I'm going to try my best, obviously not to overcomplicate things, but the gist is that if inside our fragment shader, at the moment, we want to take in some kind of texture, what we're trying to take in order to actually read from and sample a texture would be a uniform sampler 2D, and then like we would give it some name. So for example, u_texture. Now that also needs some sort of layout, except instead of a location, we specify something called a binding. So we could give it binding 0. Optionally, you can specify a set, and that's where the descriptor set comes into play. By default, it's 0, so you don't actually have to write something like this, but you could set it to like set 1, 2, I think it goes up to around 8, like that's the safe limit, but something like an NVIDIA GPU might have 32. If you launch the Vulkan hardware compatibility viewer, which comes with the SDK, then you can actually have a look at what this is. So you can see max bound descriptor sets. Obviously you can allocate as many as you want. They're just like sets of descriptors, kind of like sets of resource pointers, if you will. But in terms of how many you can actually use like within your shader, you can have 32 sets, not 32 descriptors, 32 sets. And that's important because you can see that the amount of descriptors you can have per set, so max descriptor set samplers, for example, is a lot higher than 32, of course. And that's where the whole concept of bindless resources come in as well, because if you can have that many descriptors to sample from, then obviously you can just have a huge array of all your textures and you don't really have to deal with having like a limit. But I would say for all intents and purposes, you probably shouldn't go above 8. I think Hazel has about 4 different descriptor sets. The reason why we have sets in the first place is typically because we might have resource bindings which change at different frequencies. So you can think of this kind of like there are some things that affect the scene potentially, like the camera, but then there are other things that are per object, like textures. Per object probably isn't correct to say because it's per material really, but the point is you might have different resources which change at different frequencies. So generally speaking, it makes sense to use multiple sets because you typically update all the descriptors within a set in one go. That is probably beyond the scope of everything we're doing here, so I'm not going to expand any further, but in terms of the shader code, this is fairly typical for how we would sample a texture inside our fragment shader. And then of course, if we wanted to actually sample it, we would use the texture function over here. We would pass in the sampler and then some kind of texture coordinate. Now we don't actually have texture coordinates, so this is another thing we're probably going to have to add, which I completely overlooked, to be honest, when planning this episode, because you can see it's fairly unplanned. That's kind of the point. But anyway, you would basically get a color, texture, sample. You'd get a color from the texture by using some sort of texture coordinate. Now for us, we can just use something like 0, 0 here because we have a 1x1 pixel texture, so it's not really important. And then of course we could, for example, multiply our intensity with that texture sample. And that would give us like a kind of shaded, colored object. Fs you typically don't use in GLSL, you use them in HLSL and obviously in C++ code, but I don't think F is actually even valid technically, even though most shader compilers will compile GLSL with Fs in them for floats just fine. Okay, so now that we've basically written the shader part of things, let's actually give that a compile to make sure that I haven't made any syntax errors. Looks like I have. Oh yes, okay, so this is a vec3 obviously. Here we're using texture sample, but it's a vec4 because the texture does in fact have an alpha channel as well, so we can just put a .rgb here. We could also put a .rgb on the actual texture function call and then make this a vec3, but we might as well read in the alpha and then just not use it if we don't need to. Let's compile that and we're good to go. All right, beautiful. So how do we actually create these descriptors and use them? Well, we could probably have a look at IMGUI, our favorite little consultation thing to look at here. Basically, there's a function called allocate descriptor sets, just like that. That lets us allocate a particular descriptor set, and that comes from something called a descriptor pool, and the descriptor pool is going to have a bunch of information as to how many descriptors it actually holds. So over here, inside our actual application file, so you can see that this happens inside setup Vulkan, but we're inside application GUI, not inside that IMGUI Vulkan implementation file. We have VK create descriptor pool. We've given it 1000 of each of these, right? So max sets is going to be 1000 times this much, but for each type, we can allocate 1000 samplers, so like 1000 textures to bind to or whatever from that pool. This is just memory allocation at this point, right? I want to just stress again that descriptors are not magical objects. They're literally just like a little bit of memory that tells you, hey, that texture is the one that you're using. If you're familiar with something like OpenGL, where you just straight up bind a texture to a slot, this is like the middleman. This is the thing that actually says, okay, but for slot 0, it's going to be this texture. And then of course by slot, I'm referring to this binding that we specify here. The same thing would happen if we had like some kind of uniform buffer or whatever. It doesn't matter what resource it is. Textures are just an example of a resource. We're probably going to do this with uniform buffers and storage buffers in the future as well. So we have a pool, G descriptor pool. So from here, we should be able to allocate certain descriptors. Obviously, you have to make sure that you don't allocate more than, say, 1000 of them. Typically, there would be some client-side tracking as well for like allocating descriptors. This is obviously very arbitrary, just like how many we've given it. But then you can see that from that particular pool, which is what vDescriptor pool is, it maps to the pool that we've created over here inside our application. From there, we can choose to allocate a certain amount of descriptor sets. Now, they are dependent on something called a descriptor set layout. A descriptor set layout just tells you what is actually in the set. So as I mentioned, we have like this texture here, which is implicitly set equals 0, right? So it's in set number 0. We could have 3 different textures, right? We might also have like a uniform buffer or something like that. We might have a whole range of different resources. But what determines the layout of that descriptor set? So what are the actual resources within that set? So that's what a descriptor set layout is. If we have a look at where it's actually created here, nowhere apparently, wonderful. Okay, it's not showing up in search because this file's technically not, it's included as part of a Unity build, so it's not in the solution. Anyway, point is create descriptor set layout. It's a function over here. You can see it creates one for this font sampler, but this descriptor set layout specifies that we have a particular descriptor set layout binding. There's only one descriptor there, and it's inside the fragment shader, and it's something called a combined image sampler, which just means it's like an image that you can sample from basically. And then using that binding over here, we can say that we have one binding. Now, the order of these bindings is what determines its binding index. So you can see that that's not explicitly stated because it's implicit based on the order that you have these. So if you have like 5 bindings, you'd expect them to be like 0, 1, 2, 3, 4, 5 inside this array. You can also technically have null descriptor set bindings. So that would be used most frequently if you're doing something like bindless resources. In that case, you typically have to enable something, I think, in the device that allows you to have null descriptors. Otherwise, null is actually not valid for a descriptor. So basically, if you want to create a shader that can optionally have a texture or not, you need to either set a default texture that you might not even use, like a 1x1 white texture, for example, or make sure that you have null descriptors enabled. Okay, so we're definitely going to need to do something like this. Actually, one more thing before we proceed. I want to point out that this is actually a very special case because it sets something called immutable samplers. A sampler is what determines how a texture is sampled. So are you using nearest or linear filtering? Are you wrapping? Are you not wrapping? And by wrapping, I mean not like wrapping like music, but but what happens if you exceed like the bounds of a texture? Are we wrapping? Are we going back here? Are we clamping to like the last color that we had there? That's what a sampler is. So typically you don't have that many samplers because there's only so many settings, I guess, on a sampler. It's not the actual image, it's just how you read the image, how you sample the image. Because again, that's not something that you might have a million of. It's possible to set a sampler immutably, which means you can set like a read-only kind of sampler once, like a constant sampler that is used as part of this specific layout binding. So for your combined image sampler, hey, here's like a constant one. Obviously, you still need to create an actual descriptor that has your image or your image view. But in terms of samplers, you don't need to do that if you set it as a constant over here. Again, that's something that I would probably classify as like an advanced use case, just because, I don't know, I mean, on one hand, it makes things easier, but it's just probably not the simple way of doing things, or not the expected way to do things, because you can see that generally speaking, we would create a sampler as part of this actual texture. And the reason why is because traditionally, if you set a texture, you create a descriptor that is a particular texture, it actually asks for a sampler. So this just lets you basically say, no, I'm not going to give a sampler, and in fact, it's going to use that immutable sampler instead. Okay, so let's just grab this entire function, and I'm going to put it into the renderer. I'm probably just going to put it into init over here. I'll get rid of the function declaration stuff. Now, create font sampler is going to be important, I think, because we are going to have to create this. It's just that I'm going to take this, and we're going to create it as part of our texture. So maybe at the very end of all of this, I'm just going to go ahead and create a sampler. So you can see the kinds of settings we basically have on our sampler: the minification, magnification filters, mip-map mode, LODs and anisotropy, as well as obviously the wrapping mode, which is this address mode. And then we just create it and it gives us a handle, very simple. So this becomes M sampler. We don't have an allocator, device is device, and this becomes a VK check. And just like that, we have a sampler ready to use. But the point here, I guess, is you can notice that this is linear. Like what are you going to have? You're going to have nearest instead for some textures. Maybe the way that you kind of blend between MIPs might be different. And then you might have, I don't know, different settings here, but that's it, right? It's not kind of like a per texture thing, which is why that whole immutable samplers thing exists in the first place. All right, so back to here. I'm not going to set this now, but we might revisit this whole immutable samplers thing just because I want to show you how to do it like the non-immutable samplers way. So we have a combined image sampler. There's one of them. It's going to be using the fragment shader. We've got one binding. Here are the bindings. And then we're going to create it with a VK check. I'm going to go ahead and add a descriptor set layout over here, which is going to be a null pointer. And then no need to check that result at the end because we've done it here. Allocator is also going to be null. And then finally, we also need the device. So let's go ahead and find the device over here. And there we go. Now notice how this obviously didn't involve the pool at all. This is just supposed to be a reflection of what you have in your shader. So this is what we have in our shader. So we just need to basically say that we've got this here. In a game engine, in something like Hazel, this happens automatically. We just have shader reflection data that we can read. We can create a descriptor set layout that is based on that shader code. There are more advanced use cases in which you might want to have some manual control as well in some way or another, but we're definitely not going to talk about that here. Okay, so now that we've done this, we can allocate a descriptor set based on this layout from our descriptor set pool. So to do that, because I'm not actually sure if we ended up having, I don't think we have like an allocate descriptor set function. Usually you would have something like that floating around in your renderer just because it's super useful and important to have, but also because it comes from the pool, you might have like a centralized context which contains that pool from which you want to allocate from. That descriptor pool, so it's stored inside G descriptor pool, as you can see. I think what I want to do is the following. Since application owns it at the moment, I guess it makes sense to actually basically say that I want to allocate descriptor sets. Now I'm writing sets because you can allocate more than one. We need to definitely take in a descriptor set layout and probably how many we want. So maybe I'll do UN32 count equals 1. Just so that we get 1. I've marked it as void right now because I'm not sure how we're going to store the result yet, but we will see. So from here, it's just as simple as VK allocate descriptor sets. Obviously, we need a bunch of stuff here that I will fill in a minute. We're going to go ahead and write VK device equals get device because we're going to need that obviously to actually do the allocation. And then we have the allocate info. So VK descriptor set allocate info. So I'll call this alloc info. I will initialize it as well. We'll set the structure type, descriptor set allocate info. And then we can have a look at what's actually in this struct. I'm trying to somewhat do this from memory because it's pretty simple. We've got descriptor pool, descriptor set count, and obviously the layouts. So descriptor pool is going to be our g descriptor pool. The descriptor set count is going to be count, and then descriptor set layouts or pset layouts is going to be our layout. We're then going to pass in our alloc info, and then you can see we're going to get an output, which is VK descriptor set pointer. The reason why is because there might be like a bunch of these. I think the way to probably do that is I might make 2 of these, one that just allocates 1 because that's going to be useful, and that will just be a VK descriptor set. But otherwise we might take in an std vector of VK descriptor sets out descriptors. Go ahead and create that other function. It's going to be the same thing. I'm going to copy it because obviously we don't want to allocate into the vector. This out descriptor sets will be dot resize with count, and then this would just be dot data. That's where we're writing into. Over here, it'll be a little bit of a different story. We'll just have a VK descriptor set result, which we will allocate into, and then we'll just return it. Count over here is going to be 1. Okay, so we've got 2 different functions that we can use, which is great. So back inside our renderer, we can now do application, allocate descriptor set, and the layout obviously is going to be the thing that we just created. Now, this is something that you can do like every frame if you need to. Usually people would advise against that. It's not actually that bad because again, if you think about what descriptors are, I think they're like 48 bytes or something like that. I'm not exactly sure, don't quote me on that, but they're very, very small, even though the technically correct way would be to obviously retain these instead of having to like clear the pool, because you can actually clear the pool every frame and then just reallocate stuff, right? Here are our descriptor sets. It's about to get a little bit more complicated, unfortunately. So allocate descriptor set gives us a descriptor set. So now this is a set. So we had a set layout. This is now an actual set, which is still not an individual descriptor, but we're getting close. The point of this now is to call something called VK update descriptor sets, right? So this is what lets us actually have a descriptor and then update it in the sense of like, I want this resource to point to this actual resource. So I want to write into my descriptor that it is pointing to this texture, to that specific image. So to do that, you can see we need to use something called write descriptor sets. So again, there's so many levels to this, but it does make sense. WDS is usually what people abbreviate this to. And you can see that luckily, a write descriptor set is not like some resource with like a handle or anything. It's just a struct. It's just a struct of data. It's just got all of this stuff in it. It looks like a lot, but half of it's not really used most of the time. So for example, image buffer or buffer view, you would only have like one of those set. So our resource would not be a buffer. So we wouldn't set this or this. We would just set image because it is in fact an image. The binding is important, but the array element, descriptor count, that stuff doesn't matter. So let's go ahead and create one of these. We'll set the structure type to write descriptor set. The descriptor count is going to be 1. By the way, the reason why that's important is because you could have an array. This is in fact just referring to a single one of these now finally. So if we had multiple textures, that would still be 1 because we don't have like an array of these textures. If you had an array, you would put like 32 there. Then we've got destination set, which is what we just allocated. So that's going to be our M descriptor set. This is bringing back memories. I haven't written this code in so long. Descriptor type. So a VK descriptor type is going to be one of these. It's going to be a combined image sampler for us because that's obviously what we set up here as well, by the way, inside our layout. Destination binding is going to be 0. So this refers to the binding that we have over here inside our shader and also the index of that resource within our descriptor set layout. Array element only applies to array, so that should be 0. Descriptor count we have already set to 1. So really all that remains now is to set the actual resource. So we do p image info and then we set it to our image info. Now, guess what image info is? It's not just your image view. It's actually a bunch of stuff. So if you go to what this is, you'll see that it is actually a struct. It's a struct of 3 things: a sampler, an image view, and an image layout. I kind of forgot about the image layout. This you can kind of arbitrarily set to the right thing. This is obviously the image view we created, and this is the sampler we created. If we use an immutable sampler, we wouldn't need to set this, but otherwise you can see that like the standard way to set this stuff is you include a sampler here as well. So we actually need to create one of these, and I usually create it inside the actual texture itself, because that way if we just have the image info already in the texture, then we can just write a function that returns it. So I'll write a const reference get image info const, and it will just return m image info. Now this again is just a blank struct here. So at this point we would set the image info, we'd set the image view to be like the image view, we'd set the sampler to be the sampler that we just created, and then we would set the image layout to be probably, let's see what it ends up being. So you can see that basically there's a memory barrier, there's a VK command pipeline barrier. This is way beyond the scope of what I'm trying to teach at this level, but anyway, there's a pipeline barrier here that specifies that our old layout was transfer destination optimal because we were trying to transfer like the memory into that actual GPU only memory, and then our new layout, meaning that after this pipeline barrier has fulfilled its purpose, will be image layout shader read only optimal. So this is actually that layout that we should end up with, and that's why there's a barrier to make sure that we make that layout transition. Again, layout transitions are probably one of the most complicated things in Vulkan in general, much more complicated than like the descriptors that we're talking about, but this is probably all you need to know for now. And again, if you use something like NVRHI or some sort of abstraction like situation library, then that kind of does a lot of this resource tracking and management for you, which makes things way easier, which is why I'm kind of considering pivoting towards that. Okay, so we have the image info, it's set, it's got our image view, it's got our sampler, it's got the layout. So we can now actually grab the texture and just call get image info. That returns a const reference, remember? This requires a const pointer, so we'll just put an ampersand here to get the memory address of that. And this is fine because obviously this is returning a const reference, not like a copy or anything like that. Okay, so descriptor set writes, although we can pass in the memory address of WDS, as well as actually the first parameters, the write count, so 1, and then we have descriptor copy count and copy descriptor sets, which that will just remain as 0 and null pointer. And that's it. Hopefully, by just looking at this, you can see that this is just the layout of our descriptors that are our resources. And then this is the actual thing that sets this texture to be in binding 0 inside a particular descriptor set. And since we allocated and created this descriptor set based on this layout, when it comes time to render, we can now actually not just bind like a pipeline and all of that, but we can actually call VK command bind descriptor sets into that command buffer. Now it's going to ask us for a pipeline bind point, which is just this thing here. It's going to ask us for a layout, which we have, m descriptor set layout. It's going to ask us for the set, which is 0, the set count, which is 1, the actual descriptor sets, which is going to be m descriptor set, again, could be an array, so we have to pass in that memory address here. And then the last thing is going to be the dynamic offset count and the dynamic offsets, which is just going to be 0 and null pointer in our situation. This is actually a pipeline layout, sorry, not a descriptor layout. So the pipeline layout is m pipeline layout. All right. So there we go. We now have our descriptor sets over here that we have created just once during initialization. We've created a texture and then we've created a write descriptor, which sets that descriptor. VK update descriptor sets is what actually gets it onto the GPU, which is important. So if I hit F5, I don't know what's going to happen. Probably some Vulkan validation errors, to be honest, but let's see. Where's my console? Okay, so bind descriptor sets, access violation reading that location, so something's null. Okay, so it looks like dynamic offsets. Looks like we actually need dynamic offsets. My bad. Let me have a quick look. No, actually, I don't think we should. Let's make sure that all of this worked out successfully. I didn't actually see the console. So let's make sure we have that up. Okay, so this descriptor set does seem to be allocated successfully. Nothing in the console. Update descriptor sets seems to have worked as well. Usually if that failed, you'll definitely get something in here. So that all looks fine. I really wonder what went wrong here. Okay, so the reason why we're getting this, most likely, is, I mean, pipeline layout is a little bit of a clue. The pipeline obviously needs to be aware of our descriptor set layout. It's not just the layout that we need to create over here. The pipeline needs to be aware of it. So if we go down to where we initialize our pipeline, if we find our pipeline layout and we just go to where we actually created it, you can see that the only kind of resourcey things we set were these push constant ranges. But if we have a look at what's inside that pipeline layout, it also contains our descriptor set layouts, right? And the set layout count. So we just need to make sure that those are set. So layout info.p set layouts has to be our descriptor set layout. And we also need to make sure that we specify that our set layout count is 1. So we have one descriptor set and this is its layout. Obviously, you need to make sure that you initialize the pipeline after creating that descriptor set layout. So since this stuff could happen at any point, let's just bring down our buffers and our pipeline to after we do all of this stuff. Okay, let's try again. All right, awesome. So check that out. We have a pink cube, and this pink, that we see here, this magenta, is actually coming from obviously this thing over here. So if I change that to, I think this will probably be like red, then all I have to do is recompile the C++ code and you can see it's now red. So that's pretty cool. Now this doesn't quite represent like an entire texture, so to speak. There are a couple things missing for that. First of all, texture coordinates, because we need to be able to somehow kind of project our texture onto this surface, just know like what part of the texture we should be reading for each pixel. But then also we need to read in the actual texture. I think that's going to be a pretty good exercise to leave for homework. The reason why is because I think that this video is probably a lot to take in, even if it ends up being slightly shorter than the other videos. But also I think it would be a really good exercise to the viewer as well, who's trying to learn this stuff, to actually try and load in a texture and then have it render onto this cube. To briefly explain how you would do that, first of all, you just load in the texture memory, and instead of obviously just setting this texture to be a buffer of a single color that's just 4 bytes here, you would instead set this buffer to be the actual image buffer that you loaded from the actual image on disk. If you use a format such as PNG or JPEG, then you're going to have to decode that into like a raw pixel array and upload that to the GPU. Alternatively, you could use like a GPU compressed format, but that's probably going to be beyond the scope of this as well. And then once you've done that, you'd have to go over here into your Vertex data and add a new attribute that would be your texture coordinate that you would then have to take in to your Vertex shader over here. So you'd have like a texture coordinate or a UV or whatever you want to call it, pass that into the fragment shader, and then instead of this 0, 0, you would have your actual texture coordinate be set over here when you sample the texture, and then you should see it correctly. And of course you can simply switch to like creating a cube in Blender and texturing it in Blender and then doing all the hard work there, especially if you do like UV unwrapping. You wouldn't do that manually, and then everything will work out. So I don't know, maybe we'll do that. Let me know what you guys thought of this video. From here, we have a few different directions where we could go. Obviously, this whole texture coordinate loading textures, we definitely need to do that, but are meshes something that interests you guys as well? I'm fearing that this might turn into like a general like 3D game programming series, but I guess that's what this is anyway. It's not like a 3D game engine, but we're gonna have to do some game engine things such as load 3D meshes. So if you guys wanna see like loading 3D meshes next, if you want us to just stick with this cube for now and do it all manually and just load in textures, do texture coordinates, all that stuff next time. Probably also introduce uniform buffers using descriptors as well, instead of just using push constants for things like the transform or the camera. Yeah, just let me know what you think and what you wanna see in the comment section below. Thank you guys for watching. I will see you next time. Goodbye.